Okay, this is lesson 9 of module 3, basic properties of similarity. This lesson is going to give us a chance to practice the definition of similarity that we explored in lesson 8. That we, in order to show that two figures are similar, we need to use a dilation followed by a congruence. In other words, a sequence of rigid motions, or a congruence followed by a dilation. So we need a sequence of transformations that will map one figure onto the other exactly. So the properties that we're going to explore are called the symmetric and transitive relationships. And so those sound difficult, but they're really fairly straightforward once you know what we're talking about. Okay, so these are the questions. Is similarity symmetric? Okay, so if we were to say that similarity was symmetric, we would say that if we could show that figure S was similar to figure R, then we would know that figure R is similar to figure S. Okay, so remember that when we say that figure S is similar to figure R, what we're saying is that there is a sequence of transformations, including a dilation followed by a congruence or the other way around, that would map S onto R. Okay, so if we say that R is similar to S, we're saying that there is another sequence of transformations, including a dilation and a congruence, that would map R onto S. So it's not immediately obvious that that is, but think about whether you think that's the case or not. And we're going to do this in a couple of exploratory challenges. Okay, so that's symmetric, and notice that you can kind of see the symmetry. You know, if S is similar to R, then R is similar to S. So that's the question we're asking us about that. But what does transitive mean? So transitive would be something like this. If I have figure S and it's similar to R, and then I have then I know that figure R, and we'll say and, S is similar to R, and R is similar to T, then I would know that S was similar to T. Okay, so that's the transitive property. And think about whether you think similarity would work that way. So if I have a figure, my first figure S, similar to R, and then I have another figure T that I've shown R being similar to T, then would S have to be similar to T? Would this be true? Okay, so think about what your gut reaction is to that, and then we're going to do a couple exploratory challenges. All right, so in this first exploratory challenge, we are going to look at the question here. And so let's read it. The goal is to show that if triangle ABC is similar to triangle A prime, B prime, C prime, then triangle A prime, B prime, C prime is similar to ABC. So it's answering the question of whether similarity is symmetric. And remember, so if we have a sequence of transformations that would take ABC and map it onto A prime, B prime, C prime, what we're saying is that if we can do that, then we can always find a sequence that would map A prime, B prime, C prime onto ABC. So we would only need to show similarity one way, and we would know that it works both ways. Okay, so what we're going to do is use this diagram, and we want to first check whether these are similar triangles. So we need to check the angles, because all the angles measures should be the same, and all the corresponding side lengths should have the same ratio. And so they should be equal to some scale factor. So let's first go ahead and get a protractor and measure the angles in this diagram. Okay, so you want to check angle A and A prime, make sure they're the same, B and B prime, and C prime. So go ahead and do that now. Okay, so here are some sample angle measures. If yours are off by a degree or two, that's fine. If it's much more than that, you should probably get your protractor out again and double check. These three angle measures add up to 180, which is a good double check, because the angles of a triangle should add up to 180. So by angle measures, these two triangles appear to be symmetric. So let's now we need to check the ratios of the corresponding side lengths. And as we do that, I want to give a word of caution about this diagram. I'm not real happy about this diagram. I don't like the way they've labeled the numbers on it. So I want to point it out to you, just in case I don't want it to throw you. They were not very precise in doing this. They put these numbers on for simplicity, but they're just not accurate. So looking at this side length, which is labeled as 4, and this side length, which is labeled as 4. Now these are not corresponding side lengths, but they're on the same diagram. So they clearly can't both be 4, because this one is the hypotenuse of that triangle, and this one is the hypotenuse of a different triangle. So using what you know about Pythagorean theorem, even if it's some kind of unit, which is clearly the 4 is not talking about 4 of these grid units, it's talking about some other unit, but it really can't be any unit. But nevertheless, we're going to ignore that just for this problem and check the corresponding side lengths. So let's see what that would look like. We want to check to see that, let's look at the ratio of A prime B prime to AB, and we can see A prime B prime has a length of 2 and AB has a length of 4 on our diagram here. And we can check another pair of corresponding sides, so we can look at B prime C prime compared to BC, and B prime C prime is 3 and BC is 6. Okay, so both of these ratios are now equal to 1/2. And if we check the last one, it would be A prime C prime and AC, and that one would be 4 and AC would be 8. So all three of these corresponding pairs of corresponding side lengths are in a ratio of 1 to 2. So these triangles do appear to be similar. Okay, so part B of this challenge, and I'm on the next page reading, says to describe the sequence of dilation followed by a congruence that proves that triangle ABC is similar to A prime, B prime, C prime. So what I am first going to do is to do the dilation, because it tells me to do that. It says a dilation followed by a congruence. Now we learned in lesson 8 that we can do these in any order, but since this exercise is asking me to do the dilation first, I'm going to do that. Okay, so I'm going to do a dilation from center O, with a scale factor of 1/2. And the reason I know to use 1/2 is because we just checked all the ratios of the side lengths, and 1/2 was that ratio. So I'm going to start from the origin and dilate point A, B, and C by a scale factor of 1/2, and this is what I would get. Okay, so this is my new triangle that I dilated from center O with a scale factor of 1/2. I used the coordinates. You could also, use rays, of course, coming out from the origin through the points, like so. Okay. But when I'm on the coordinate grid like this, the easiest thing really is just to multiply the coordinates by the scale factor. Okay, so now that I've done the dilation, I'm going to translate this triangle because I want to match one of the vertices up. So this is A, we can call it double prime, I guess. And this one is C, and this is our B right here. So what I'm going to do is to translate and get one of the vertices to match up. So we're going to we'll go with A. We'll map A over since they're the closest. So I'm going to go, that will be my translation to get over to A. So this translation would be 1, 2, 3, 4, 5 units to the right and 2 units up. Okay. So after my translation, you can see where the triangle moved to, and now to finish it, I'm going to rotate it D degrees, however many degrees needed to, oh, I've got the wrong tool here. I want to get AC, I still have it. I go all the way around this far so that my segment AC matches up with A prime, C prime. So I would have, and you would describe this on your challenge, you would have had something like, we had the dilation, and then the translation, and then the rotation to complete it until line AC mapped up with A prime, C prime. Okay. Okay, so now we had a sequence that took us from ABC on to A prime, B prime, C prime. And we did that successfully with a dilation, translation, and rotation. Now we're going to try to come back this way and see what that sequence would look like. And this is part C of our challenge on the next page. Okay, so for to go back the other direction, we'll be starting with this triangle here, A prime, B prime, C prime, and we're going to do a dilation followed by a congruence. And so the first thing that we're going to need to do is dilate this triangle so that it's the same size. So that means that to dilate it with the scale factor of R equals 2. Okay, so what that's going to mean is that I don't have room on my screen and you have room on your paper, but we need to go, it's to dilate with a scale factor of 2 is going to push this triangle out way out here, but even bigger than that, right? So what I'm going to do here is, and you can draw this on your paper, but I'm going to find the coordinates of the dilated points. So A double prime, B double prime, and C double prime will have a set of coordinates. So since A started out at 3, 5, the dilation of A would be at 6, 10. And since, which actually does fit on my grid, it's about right there. 6, 10 would be there. And B double prime would go from 5, the x-coordinate is 5, so it'd go to 10. And the y-coordinate is 6, so it'd go to 12. So that would be 10, 12, somewhere up, 9, 10, 12, somewhere up around here, right here. And for C double prime, the x-coordinate is 4, it would become 8. The y-coordinate is 9, so it would become 18. 2 times 9. So 8, 18 is way off my grid, somewhere up there, okay? So we can begin to draw the triangle. It would be something like that up there. Okay, so that would be our dilated triangle, and then we would need to get it mapped with the series of rigid motions now onto ABC. So the translation I see would be this one here, and we can think about how to describe that translation. So by counting, I see that it's 10 units to the left and 4 units down. So I've translated my triangle there, and so it would be, this was A, B, and C was up there. So I would have my A and A prime would match up. B would be somewhere like that. This would be my B double prime here. A's are matched up. So then you can see I want to take this and I want to rotate my triangle all the way to here so that A double prime, C double prime, and AC match up, and then the triangles are mapped onto one another. Okay, so just to summarize for you what you should have in part B, and it's kind of interesting to look at this, is so in part B we dilated with a scale factor of 1/2, and we translated 5 units right and 2 units up. Then we rotated around point A d degrees until AC coincided with A prime, C prime. Okay, and then in showing the other congruency, we dilated the smaller triangle from center O with R equals 2, so we enlarged it. Then we had to translate 10 units left and 4 units down. Then we rotated around point A until the A prime, C prime coincided with AC. Okay, so I want you to see the difference here. So we had, we're showing the similarity in 2 different directions, and so notice our scale factors are reciprocals of each other. Our translation is opposite and scaled up. So 5 units right becomes 10 units left, 2 units up becomes 4 units down, and then we have the rotation. So you should answer this question, which says, Is it true that triangle ABC is similar to triangle A prime, B prime, C prime? And A prime, B prime, C prime is similar to ABC. Why do you think this is so? And so you should have something to the effect of that even though we did used a different scale factor and a different sequence of transformations, we still were able to map the two triangles on top of each other no matter which one we started with. Okay, our next exploratory challenge is going to get at whether similarity is transitive. So what we're going to do in part A in this diagram, you are going to show that triangle ABC is similar to A prime, B prime, C prime. And so you'll need to find a dilation and a congruence that will map ABC to A prime, B prime, C prime. And then in part B, we're going to start with A prime, B prime, C prime and prove it similar to A double prime, B double prime, C double prime. So we're going to take this one, map it to here. Then we're going to have a separate sequence that takes this to map it to here. And then in the third, we're going to see if we can take ABC and map it to A double prime, C double prime. So you can work on that on your own. There'll be 3 separate sequences and all proving different pairs of these triangles similar to one another. All right, so go ahead and work on that and then come back and we'll compare our answers or our work together. All right, so if I'm going to go from ABC to A prime, B prime, C prime, I can look at it and see that it's going to be a scale factor of 3 because I'm going from 3 to 9. This side is 1 to 3 and 2 to 6. So I need to dilate this triangle by a scale factor of 3. So I'm going to put there what that would look like. Okay, so my dilation gets me to this triangle here with the green vertices. And now in order to finish the mapping, I just need to translate point, let me get another color here. We'll go up here. So point C needs to be mapped up to there. You can see it from point A mapped up to there. So that translation would be 5 units up. So I dilated with a scale factor of 3 and translated the new triangle 5 units up. Okay, so that's how you should have described the similarity that proves ABC similar to A prime, B prime, C prime. So now I'm going to show you how you would have done part B to show A prime, B prime, C prime similar to A double prime, B double prime, C double prime. Okay, so for this next one, the scale factor is a little trickier. So I'm going to write it out. So my dilated, I'm going to compare B double prime, C double prime segment to BC. And so my scale factor is going to be the dilated length, which would be this one, 2 over the original length of 3. So my scale factor is 2/3. And I can check that with another set of lengths, the 6 and the 9. Dilated length is 6, original is 9, and so that also is 2/3. Okay, so the dilated triangle ABC looks something like this. It's the coordinates are not exact. This is 7 1/3 on the y, and this is 5 1/3 and 3 1/3. Okay, so I used the coordinates and I dilated that triangle. So now we need to map this triangle onto this one. So what I could see, this is coordinate A or A prime, and I'm going to use a translation to translate it down to A double prime, and then we'll rotate. So this triangle here will move. Like so. So what is that translation? Well, it's down and to the right. So the translation was about 3 1/3 units down and 5 units to the right. Okay, and so I'm not quite done yet because I need to translate or rotate, sorry, until around that angle. So we're going to rotate it up so that the triangle coincides. Okay, so you would be using more precise language as you describe these rotations, but I'm just doing this to check your work here. So we've got one more to do. So for part C, we're going to verify that ABC can be mapped onto A double prime, B double prime, C double prime. And once we do that, we've shown the transitive property because we've already shown this triangle similar to this one and this one similar to this one. So can I assume then that this triangle is similar to that triangle? So we're going to show it, and then that verifies the transitive property for similarity. All right, so let's see what that would look like. Go ahead and do it on your own and then check your work against mine. Okay, so in looking at triangle ABC and A double prime, B double prime, C double prime, I see that the scale factor is 2. And so I have dilated triangle ABC, but this time by a scale factor of 2, and to get it to the same size as this one. And so this is what that would look like. And now I'm going to do my sequence of rigid motions to translate it over there. So it looks like, or to map it onto the other triangle. So it looks like we can do a translation again to match vertex A to A double prime. So that would be 1, 2, 3, 4, 5 units to the right, and that would move the triangle like so. Okay, and then the only thing left to do, so all these points moved over 5, like so. So my new triangle's here, and now, as I did in the other cases, I'm going to rotate it around so that it maps onto A double prime, B double prime, C double prime. Okay, so what part D asks is it true that if a triangle ABC is similar to A prime, B prime, C prime, and let me get rid of my marks here so we can talk about this. There we go. If this is similar to this, and A prime, B prime, C prime is similar to A double prime, then the first one is similar to the third. So why do you think this is so? We showed that it was true, and you could talk about You could talk about what a dilation does. A dilation preserves angle measures. So if I dilated going this way, the angle measures would be preserved. So therefore, if I then could show that these angle measures were the same by a dilation and a congruence, then I would know that they're all the same. So the same thing would go for the ratios of side lengths. If these are all proportionate and these are proportionate, then there would be some scale factor that would relate these two. So notice this was a scale factor of 3 going this way, and of 2/3 going this way, and then a scale factor of 2 going between these two. So even though the scale factors between the pairs of triangles are different, they're still in proportion to one another. We can find the scale factor. So your answer for part D could discuss some of those ideas about dilations and what it means for these triangles to be the same shape. In other words, their angles stay the same, but the side lengths can change, but they change proportionately. Okay. Okay, so this would be the summary of what we did. We showed that similarity is a symmetric relation, so that if one figure is similar to another, then we can be sure that it works the other way around, that the second figure is similar to the first, and that we could find that sequence of transformations that would show that to be true. It's also transitive, so that means, like it says here, if S is similar to T, T is similar to U, then we know that S is similar to U. Okay, so go ahead and work on the problem set and the exit ticket. A warning about the exit ticket, the triangles there, you have to rely on the given side lengths to check the similarity. They are not drawn to scale. So you'll find 3 of the triangles will be similar and the other 2 are not. So I just wanted to give you that clue because it kind of threw me, because they're definitely not drawn to scale. So work on the exit ticket, check your work, and then go on to the problem set. Okay.